Hello students, our next topic is nuclear reactions. There are different types of nuclear reactions. First one is elastic scattering. What is meant by nuclear reaction? When a nuclei come to the potential field of another nuclei, they interact with each other. This is really mentioned as nuclear reaction. First one is elastic scattering. The incident particle strikes the target nuclei and leaves without energy loss. But there will be an altering in the direction of motion or scattering is possible. So scattering of alpha particle in gold is an example of nuclear reaction. Here is one example. Second type is inelastic scattering. The scattered particle may lose kinetic energy in excess of that required for an elastic collision with the nucleus. The loss in energy is used to excite the nucleus to a higher quantum state. So there is an excitation possible for the nuclei using inelastic scattering. After some time, the excited nuclei come back to the ground state by emitting the excess energy in the form of gamma radiation. This is a type of nuclear reaction. Here is an example: lithium transforming into a higher excited state and finally releasing a gamma photon. Next is the disintegration. On striking the target nuclei, the incident particle is absorbed and a different particle is ejected. Here is an example. That is disintegration. Next is photodisintegration. When the gamma rays are absorbed by the target nuclei, exciting into a higher quantum state, the energy is enough, one or more particles may be liberated. So, by the absorption, there is an absorption of a photon, disintegration occurs by absorption of gamma radiation. Next is radiative capture. A particle may combine with the nucleus to produce a new nucleus or a compound nucleus which is in the excited state. The excess energy is emitted in the form of gamma ray photons. So, here too there is an absorption of a target or incident particle and it goes to a higher excited state, and after that it releases a gamma photon. Next is direct reactions. A collision of an incident particle with the nucleus may immediately pull one of the nucleus out of the target nuclei by the so-called picking reactions. In the inverse process, a bombarding particle composed of more than one nucleus may lose one of them to the target by the stripping reaction. Such reactions are called direct reactions. Next is heavy ion reaction. Nuclear reactions induced by heavy ions exhibit the characteristic both of compound nucleus and of the stripping and the pickup mechanism. Here is an example. So these are the 7 types of nuclear reaction. Now, the compound nucleus formation. In many of the nuclear reactions stated above, an incident particle strikes the target nucleus. This is common for most of the nuclear reactions, and the two combine to form a new nucleus that is called the compound nucleus. In 1936, Bohr proposed the theory of compound nucleus, which has been extremely useful in the correlation and interpretation of nuclear reaction. According to Bohr, the nuclear reactions take place in 2 distinct and independent stages. Nuclear reactions take place in 2 distinct and independent stages. First stage is of a compound nucleus C, and the second is the disintegration of the compound nucleus into its products. So, the compound nucleus is first formed and after that it is disintegrated. So, X plus X is equal to C star. The instant particle captured by the nucleus gives up its energy to the few nucleons, and the result of and as a result of the interaction of these nucleons with all others, energy is quickly distributed among all the nucleus of the compound nucleus. The new nucleus thus formed is in the excited state, C star. Now the mode of disintegration of C star into Y plus Y is independent of the mode of formation. Okay? The mode of formation is not depending the mode of disintegration. And it depends only on its energy, the energy of C star, angular momentum and parity. A compound nucleus once formed can decay in a number of different ways. So here you can see sodium and helium interacting to form aluminium. This is the first step, formation of a compound nucleus, and it is can be disintegrated in 4 different ways. Okay, this depends on the energy, angular momentum and parity of the compound nucleus formed. Here is another example. In this example, there are different ways to form this compound nucleus. There are 6 different ways to form the compound nucleus and then 4 different ways for disintegration of this compound nucleus. So these are the 6 ways for the formation of this compound nucleus, and these are the 4 methods of disintegration of this compound nucleus. Next is resonance. We found that in nuclear reactions, compound nucleus is formed which is in excited state. The excited state formation depends upon the incident energy of the bombarding particle. By studying the cross-section for the reaction, we can gather information regarding the mean life of the excited state. When a graph is drawn between incident energy of the bombarding particle and the cross-section of the reaction, which I have dealt earlier on the cross-section section, a peak is obtained in the graph. Such a peak is called the resonance, similar to the resonance in LCS. The name resonance here is justifiable because a compound nucleus is formed when the incident energy coincides with one of the energy levels of the nuclei. Okay, this is the explanation for resonance. From the resonance curve, we can calculate the mean lifetime of the excited state. So according to Heisenberg's uncertainty principle, delta E into delta T is approximately Hz. So if we take the uncertainty in time delta T as the mean lifetime tau of the excited state and the level with half maximum, gamma becomes the sprint or the uncertainty energy. Thus we have tau into gamma is approximately equal to h cross of tau. The mean lifetime is equal to h cross by gamma. Thus we can find out the mean lifetime of the excited state. Next is the center of mass coordinate system. Most of the experiments of nuclear reactions are carried out in a laboratory in which one nucleus is at rest, called the target nucleus, and the other one striking it. Such a setup in which the nucleus collides with another nucleus at rest is called a laboratory frame. Here we take it as a laboratory frame. This is a lab frame or also called lab frame. This means that coordinate system is fixed in the laboratory. In other words, the coordinate system is stationary with respect to the observer. This is because the observer is at rest with respect to the lab. So the origin of the lab frame is the target nucleus. So there is one more other frame called the center of mass frame, in short CM frame, with respect to which nucleus reactions can be described. So the second method is by center of mass frame. The coordinate system is fixed with respect to the center of mass. That is, the origin of the coordinate system is taken as the center of mass of the system. This we are going to discuss. So first of all, we consider the lab frame. Consider two masses Ma moving with speed UA. It approaches a particle MB. UB, it is at rest. This is the lab frame. MB is the mass. Its speed is 0 before collision. Now what is the center of mass? RCM, center of mass coordinate. RCM is equal to MARA plus MBRB by MA plus MB, where RA, RB are the position vectors. On differentiating, you get it as MA dRA by dt, MB dRB by dt by MA plus MB. and we substitute it as UA and UB. Since UB is equal to 0, velocity of center of mass is equal to ma UA by ma plus mb. Vcm is the center of mass. Speed. In lab frame, the total kinetic energy is that of the incident particle only. Kinetic energy in lab frame is equal to half ma va square. Next is the center of mass frame. So we are considering two particles moving with velocities UA dash and UB dash. So the center of mass position vector R dash Cm is equal to MARA dash plus MBRB dash by MA plus MB. That is equal to 0. We are choosing the position of the frame of reference at the center of mass. So we have from this equation we get MA RA dash is equal to minus MB RB dash, where RA dash and RB dash are the position vectors. On differentiating this equation, MA dR dash by RA dash by dt is equal to minus MB dR R dash B by dt. So you get it as MA U dash A is equal to minus MB UB dash. This means that in center of mass frame, the direction of motion of the two particles will be opposite to each other. That is a negative sign. What is the relation between velocities in lab frame and that of the center of mass frame? From this relation, MA and MB are the two particles. This is the center of mass. This is RB dash and this is RA dash. Here it is RA and here it is RB. This is VT. So you can write RA is equal to RA dash plus VT and RB is equal to RB dash plus VT. Differentiating this equation, you get UA is equal to UA dash plus V and UB is equal to UB dash plus V. Or UA dash is equal to UA minus V. Therefore, and UB dash is equal to minus V. Since UB is equal to 0. Now we can calculate the total kinetic energy of the two particles in a center of mass. So kinetic energy center of mass is equal to half ma UA dash square plus half mb UB dash square. UA substitute UA dash as UA minus V. Solving. Also put UA from this equation. Put UA here in this equation. You get it as final equation. Kinetic energy center of mass is equal to kinetic energy lab minus MAV square minus MBV square plus half MAV square plus half MBV square, or kinetic energy lab minus half into MA plus MB into V square. So we can finally get the result as kinetic energy center of mass is equal to MB by MA plus MB kinetic energy lab. These are the equation connecting the kinetic energy of lab system and the kinetic energy of center of mass system. A Q value of the reaction is defined as the difference between the rest energies of A and B and the rest energies of C and D. That is, Q is equal to MA plus MB minus MC minus MD C square. If Q is positive, energy is given by the reaction, is given off by the reaction. Q is negative, enough kinetic energy must be provided by the reacting particle so that Ke Cm plus Q should be greater than or equal to 0. So next we move on to our familiar topics, fission, fusion, nuclear reactors, etc. I am not going to explain this in detail. You go through these notes and prepare a note by yourself. Here you can see the nuclear fission and the important points regarding fission. Next is the thermal slow neutrons, critical and the parameter K factor which decides the reaction. Then here is the nuclear reactors, the important parts of the nuclear reactor. Coolants, control load. What are the uses? Next is a breeder reactor. Here in the present for us, the presence of fast neutrons, such reactors are working. You go through this. This is different from the usual thermal reactors. Next is nuclear fusion reaction. Important. Nuclear fusion in stars. The proton-proton cycle and the carbon-nitrogen cycle resulting in fusion.